A little bit about Wi-Fi. And we're a relatively small lab, about 55 to 60 people, about 40 are PhDs. But we have a very active internship program. So we engage with academia to take lots of interns, about 100 interns last year, split between India and outside India. That is, people from outside India come to the internships at the Bangalore lab. In addition, we have what we call as research assistants and of course postdocs. Research assistants are, you might sort of call them pre-docs. They are people we hire after bachelor's or master's years. I'm not going to read all of this out, but I'll just focus on the area that I lead, which is mobility network systems, and give you a sampling of some of the projects we've been doing. We'll just talk about 3 projects and then move on to the broader perspective. So one of the areas that we've been working on is indoor localization, where the problem is you're trying to sort of provide a GPS-like capability indoors where GPS doesn't work. So you want to enable them to inside a mall or inside an airport, locate themselves, help them navigate and so on. But GPS doesn't work because the signal is too weak, there's multi-path and a lot of issues. So one of the ideas is to use the Wi-Fi network and the fact that Wi-Fi signals are available everywhere to do indoor localization, and that is something that we've been working on. But the biggest problem with doing that is, one of the big problems is the need for calibration. So when you go to a new space, you have to do extensive measurements to calibrate the space, and those measurements would have to be repeated every time something changes in the space, like the crowding level has changed, or the layout has changed, or the positioning of the access points has changed, and so on. So we came up with some techniques to use a combination of modeling and crowdsourcing to solve this problem by leveraging the simple observation that today most of us have a smartphone with us which is Wi-Fi capable, and that smartphone goes with us wherever we go. So essentially, software running on this device can make Wi-Fi measurements, but of course it wouldn't know where the measurement was made, so we need to come up with some clever ways of figuring that out. So I'm not going to talk in detail, but if you're interested, there's a paper that appeared at a conference last year, that has the details. But the point I want to point out is that we worked with students here. So we had an intern from IIT Bombay who was a co-author of the paper with us. And also this work beyond the publication and the research also has resulted in a technology transfer inside Microsoft to Windows Phone. So a lot of our work has a flavor where we do a combination of what you might call as pure research, where we try to solve a problem and write a paper on it, but also try to have an impact on technology. Another example is this idea of Wi-Fi over narrow channels. So if you're sort of following Wi-Fi trends, the trend is towards wider and wider channels. So traditional Wi-Fi was 20 megahertz, then the channel wanting to do 40 megahertz, now 80 megahertz and so on. So people are sort of essentially going wider and wider. Although that might seem like a good thing, it actually is quite problematic for a couple of reasons. One is that as the channel gets wider and wider, there are some overheads associated with sending a frame on the channel that remain fixed, that don't shrink with time, don't shrink with the channel width. So over time, as the channel gets wider, what you find is that much of the airtime is just the overhead. The actual data transmission is 10% of the airtime. 90% is just overhead, which is obviously a very undesirable state. The second problem is that if you look at some of the newer spectrum regions that are being opened up, like the so-called TV band white spaces, which are low frequency, relatively low frequency spectrum that propagate very nicely, you don't tend to get big chunk of spectrum. You get slivers of spectrum. There may be some amount of spectrum free here and some other amount free there and so on. So you need to come up with a way of actually communicating over a bunch of narrow channels. That's what Wi-Fi and CMI is to do. And again, if you're interested, there's a paper on this that talks about this. And so we did this work at Microsoft Research, but then going forward, we are looking to collaborate with IIT Madras and IIT Bombay on actually building a test bed and deploying some of these research ideas or sort of in the white space spectrum. Right? So hopefully that will lead to something interesting. This is my final example, and then I will talk about my perspective. It's a very different domain. This is on click for online advertising networks. Right? All of us know how Google makes money. Right? Essentially, every time you click on an ad on that is sort of being presented by Google, either on their site or some third-party site, they make money. Right? And the reason they make money is that the advertiser has to pay. Essentially, roughly, for every click, there's a certain amount of pay. So there is a lot of incentives. If I'm a publisher and I'm hosting ads, there's a lot of incentive for me to do click fraud. Essentially, generate a lot of clicks on my site so that the advertiser has to pay, of course, Google, but also has to pay the publisher that's hosting the ad. So far, there has been no work that actually quantifies the extent of click fraud in online advertising networks. And the only people who might know would be Google and Microsoft, Bing and so on. But if you are a third party, for example, let's say you're an academic researcher, how do you even quantify this? So my colleague, David Gohar, came up with some clever ideas. And again, I will not talk about details, but let me just give you one simple example here. I want better to pursue to get the pointer. Okay. Think of this here. This is what he calls a bait ad. Right? I mean, if you look at this, it makes no sense. There's a bunch of English words that are being strung together. But the way click fraud is done is not usually by having people go and click. Right? It's actually you have a bot that's clicking. The bot, unless it's very smart, can't tell the difference between this and a legitimate ad. Whereas a human user who looks at this will click on this. So you can then distinguish between bot clicks and human clicks by creating this bait ad, for example. Just one example. Now this is something where we collaborated with the university, or we are collaborating with the university outside India, and also we have had a technology transfer to Microsoft. So I just wanted to give a quick flavor of the kind of work we do, which is a mix of it's sort of systems research, that the mix of academic style, sort of publication-driven research, and technology impact, but often with collaborations with academia, both in India and elsewhere. So now let me give you some perspective, some thoughts on two topics. First is research, various universities in India, and also about education at a much broader set of institutions in the country. Again, I just want to repeat the caveat I mentioned earlier. This is all based on my limited perspective as a computer science person who has been almost always in the industry. So, what seems to be the case is that if you look at computer science departments at many of the IITs, IITs, and so on, there's a very strong emphasis on theory. You have sort of very strong theory work happening, very strong theoreticians, but not nearly as much emphasis on the applied areas. It's much, much weaker. In both in terms of number of people, faculty they have, also in terms of the amount of output they are producing in the applied areas. I think that's a huge problem, and it's really holding back sort of academia in general. And so there's really a need to dramatically scale up what I would call sort of systems-oriented, hands-on work, right? Where people are actually taking ideas and building prototypes, deploying them, testing out, not building products, but actually taking ideas beyond the lab and actually trying them out. And there are huge benefits in multiple dimensions. It obviously greatly enhances the impact you can have. The impact is beyond academia. The impact is on industry, on policy, on the government, on society at large. It makes the students much better prepared when they graduate. Right? When they leave and go to industry for a job, they would actually have skills that industry would value, as opposed to someone who has not done that. And that can actually build up a cycle where then you might be able to attract more talent and more funding and so on. Essentially, you can sort of build up. What this requires, among other things, is a huge culture change, I think. I mentioned this because I will not name names and I will not even name the institution, but one of the sort of few systems professors at one of the top universities in India told me that he gets no respect in this department, right? Because people look at what he says and, oh, you're just building some stuff. I mean, what is intellectually deep there? What is intellectually challenging there, right? I mean, isn't it just engineering? What's research here? I think that's a very wrong way of looking at things, because as I mentioned one quick example in the next couple of slides, but actually building something and trying it out will teach you so many things that you wouldn't have otherwise known, that the quality of the work and the impact of the work can be dramatically different. I think this kind of work, systems work, is worthy of the best research minds that are available. So let me take one example. So, if you've been following wireless networks and so on, there's this topic of wireless ad hoc networks, right? I picked this because, so I went and did a Google Scholar search on, I guess, ad hoc networks. Can anyone guess how many hits I got? I guess you can read it there, but you can't read it. Can anyone guess how many? How many?
Millions.
Yeah, that's great. Okay. 1.6 million papers on this topic. Okay? Which is staggering. The reason I picked this is that I think one or two of those are my papers too, so I don't feel so bad picking on this topic. So this is how, I mean, sounds like, okay, people have worked everything out. I mean, you've written 1.6 million papers on, collectively on a topic, maybe everything that you need to know has been worked out and everything just works. Well, about 10 years ago, people started, roughly 10 years ago, a lot of companies, Microsoft, folks at MIT, a lot of people started building this sort of multi-hop wireless mesh network. The idea was you're trying to reach someone, they don't have connectivity or whatever, so you hop multiple times with Wi-Fi or something and get to them. Right? So essentially you build a mesh network that provides connectivity. But people tried, we tried it at Microsoft, a lot of people tried, and gave up. Essentially those efforts have been largely a failure. In meshes like military applications, so they may exist, but as a viable system that can be built and maintained, it's been largely a failure. And that's because there were lots of problems that were hidden and people were just doing the theory and doing even simulations. It's only when they actually started building things, measuring real-world wireless propagation when you're sitting in a house with a concrete construction and you're trying to send a signal to a repeater node somewhere else, but behind another wall, what happened? In particular, for example, 2.4 gigahertz wireless Wi-Fi has poor reach, poor coverage. And so you try to build a multi-hop network, pretty soon your performance is through the floor, issues with maintaining the network, lots of issues. So after this struggle, a lot of the same people came to the realization that we need to fix something fundamental here. We can't sort of take something that's designed to be a wireless LAN and try to build this mesh network. Let's actually shift to a different part of the spectrum. Right? So in the last 5 or 6 years, there's been a lot of interest in TV band white space networks. So the idea there is sub-gigahertz spectrum, which is nice because it propagates nicely, propagates well. That is lying largely unused in lots of places in the world. Right? They've been allocated to various people, but they're not being used. Now there is an owner, so you can't just take away the spectrum, but you could dynamically use spectrum when it's not being used, and actually build a network that way. The big advantage, as I mentioned, is that you get much better reach. And that idea, now if you build a network like that, you don't need to go multi-hop. You can have a single tower that's got a reach of a kilometer or even multiple kilometers. Right? So you can afford to build towers that actually provide coverage that way. So you have a much simpler architecture, more a cellular-like architecture, and can provide much better coverage. And so this is something that a lot of regulatory bodies around the world are getting on board on. So the US FCC was pioneered this 5 years ago. Ofcom is the FCC equivalent in the UK. TRAI in India also, I was speaking with Professor Jamadagni from IISc, who's involved in TRAI, and he mentioned they have started to think about this stuff. A lot of companies are interested, Google, Microsoft, and others. So in some sense, if you had stopped at those 1.6 million papers, you wouldn't have realized that the real world issues, and you would not have sort of found this new direction. Now, one other point I should make is, even if you're a theoretician, it often makes sense to reach beyond the theory and actually look at an application of the theory and sort of maybe through collaboration or maybe yourself. And I've just picked out some prominent examples of people who are very theoreticians. Ben Brandrock is a theorist at UCLA. His lab built one of the first nodes of the ARPANET, which is the precursor to the internet, right? Way back in the late 1960s. Shamir, many of you probably heard of him, is the co-inventor of RSA. He has taken it beyond and actually built RSA as an underpinning of secure communications in the internet today. Tom Layton, maybe you've not heard of him, but he's an applied mathematician at MIT, so a theoretician really. But he took some of his theory work on consistent hashing and turned it into a company called Akamai, which is the largest content distribution network in the world. Anytime you go to a website today, or many websites, you go to CNN's website, you go to a bunch of your content is coming from Akamai's network. Actually, it's really a system. It's probably one of the largest distributed systems in the world. But it was founded by a theoretician with the sort of basic ideas coming from there. So, again, I'm trying to make the point that there's huge benefits, in fact, to be had by technology. So this is my last slide on this. So the question is, okay, how do we get from where we are to there? Right? I mean, it's sort of fine to talk about MIT and so on and say, okay, we should do that. I think you can actually do quite well with the resources we have. Right? So even if the research pool in academia is limited, in terms of PhD level students and so on, you have BTech students and you have MTech students. And you can actually get a surprising amount done to a course project, to some extra effort, or to a BTech thesis or an MTech thesis. Right? And I speak from personal experience. I did a course project almost 20 years ago that resulted in a paper that won the best paper award at a fairly prominent conference. Right? Of course, there was extra work. It was not like I did the course and then the paper happened. You got onto the problem and then you continue in the technological university, and all the engineering colleges in the state come under that university. Right? And I guess in Tamil Nadu it's another university, and there's hundreds of colleges under that. So we're talking about those colleges. So essentially, so this is the slide. So essentially, the idea here is to take a leaf out of MOOCs, or massively open online courseware, right? Coursera and so on. But the problem with Coursera and so on is that they're very good, but they're in some sense disconnected from the university. What they're trying to do, what my colleagues are trying to do with MEC, massively involved classrooms, is to actually come up with a way of taking online content and melding it with, they call it the blended learning. So melding it with the classroom experience, so that it enhances the classroom experience as opposed to becomes an alternative. Right? I can't do justice to the details here, but if you're interested, and they're doing a video, actually this is completed. They did a pilot in Karnataka with PTU. They got 2,000. Of course, a bunch of them dropped off. They ended up with a few hundred, still a good number. And now they're scaling it up and they're trying to do the content. But they're also interested in hearing from universities and colleges that would like to try this out. So if you're interested, you should visit this website, mecr.org, and get in touch with that. That's all I have. Thank you.